Hello everyone, let's continue. So before even getting into the spice simulation for variation of CMOS inverter, we will try to identify the sources of variation first, because unless and until we identify the parameters, the exact parameters that is basically varying the width and length of your CMOS inverter, we might not be able to conclude things in a better way. So let's try to identify the sources of variation first, and then we will simulate the same CMOS inverter for a variety of standard inputs, and then see how does the CMOS inverter is immune to those variation. So the first sources of variation is the etching process. So etching is basically a fabrication step. It's a very important fabrication step, and the etching is the process that actually defines your structure. It defines the width and the height of your structures. So it's very important. This particular stage is very important, and defining, and based on the structures that gets defined by this process, it directly impacts your delay, and we'll look into how does this process will directly impact the delay of a cell. Okay, so let's begin with that. So we have this single inverter. So let's first look into how the etching process can affect the behavior of a single inverter, and that can be always propagated to the behavior of any logic cell, because CMOS inverter is the basic building block behind any of the logic cell. So this inverter, if you try to open it, it will have PMOS at the top and NMOS at the bottom. These are the transistors. But if you deep dive into the transistors, if you see this is nothing but the PMOS diffusion area or the P diffusion area. This is the N diffusion area, and this is the polysilicon gate, and these are all metal lines. So this is the basically fabrication elements of the transistors. Okay, so if you try to look into the layout of this particular inverter, it looks something like this. So you have a P diffusion region which is of some width and height. You have this polysilicon area, which is of certain width and height. You had this input and output. So basically blue lines it indicates the metals over here. The green indicates the P diffusion, the yellow indicates the N diffusion area, the red color indicates the polysilicon area, and yeah, and these are the contacts. The black cross that you see, these are nothing but your contacts. So each particular color identifies each metal layer. So for example, let's say for example, this is metal 1. This could be, the green color could be metal 2, the yellow color could be metal 3, and this could be metal 4, and so on. So each particular color indicates a particular metal layer. Okay, and how do we get this particular shapes on each and every metal layer? That is through etching. That's basically the etching process. The etching process will define the structures that you see. If it's a rectangular, it will be decided by the etching process. It will be decided how well the etching has been done. Okay, and if you look into this particular gate, so this is your PMOS gate, and this area is your NMOS gate, and this is the gate length. Usually I have talked about the term gate length. So this is the gate length. This basically defines at which node you are, whether you are at 20 nanometer or 30 nanometer or 45 nanometers, 65 nanometers. So this is that particular node that will decide at which technology node you are in. Okay, and this is the width of the gate. So there is something called as W by L ratio. We have been always seeing this W by L in any of the equations. So this is the width. So basically width identifies the overlap area of the gate on the P diffusion region. So that is what defines your width. Okay, so with all that basic things in mind, let's look into this was the single inverter. Let's look into a chain of inverter. Okay, what happens when we try to fabricate a chain of inverter? So let's say this is the chain of inverter, and this is the input, or this is the output, or this could be also a part of your data path. So for example, there could be a flip-flop which is sitting over here. Okay, there could be a flip-flop which is sitting over here, and this could be a part of your data path, or this can also be a part of your clock path. This could be the clock port, and this could be the D flip-flop pin, or whatever. This can be a part of any of your circuit, and this is how it looks like. So if you try to fabricate this particular inverter chain, this is how it will look like. Okay, so let's look into one of the elements. Let's take this particular element out of the circuit and see how well it will get fabricated. So ideally, if you see, if there had been a very ideal mask, ideal fabrication scenario, this is how the structure would have been looked like. Okay, but in real case scenario, because we are always dealing with real elements in a fabrication process, so fabrication is basically a lab where you have a lot of things. You have chemicals running, you have water, you have there are gases running, so those things are all there in the fabrication lab. Due to those effects, the structure, the ideal structure which had been like this, can look like this. It can look distorted, and the etching, this the edges of this particular mask, how well defined are these edges, that will be defined by our etching process. So let's say the etching process that we did, that creates a mask which is something like this. Okay, so if you see the L over here, the shape is a bit distorted. Even the W shape is a bit distorted. So ideally it would have would look like this, but now it looks something like this. So one impact that you see, if you see the overlap area, if you see the area of this particular section is W into L, that is, it has got, let's say, some area W into L, and this will be W dash L dash. The area will be different, because if you see the edges over here, the edges are not well structured compared to this one. So this will have a well defined area, but this will not have a well defined area. Okay, and on the other hand, you will have a length which is like this, you have a width which is like this. So if you try to calculate the actual length over here, and if you try to calculate the actual length over here, they will differ with some amount. Okay, so this is one of the variation. And if in this case, if this is a small variation that we see on one inverter, just imagine if there are so many inverters that are connected back to back, the amount of variations that you will see. So you will see this kind of variations a lot happening on a chain of inverter which is fabricated on a chip. Okay, and that to not only a small area, because the chip is being getting fabricated on a larger area, so we'll find similar kind of distortions. Basically the distortions are not, they are not repetitive. There could be a different kind of distortion for this inverter, there could be a different kind of distortion for this inverter, and so on. Okay, so let's look into another inverter. So for example, if you look into this particular section, the center area, the gates in the middle have got same structure either side. Okay, so for example, this gate has got an inverter over here, it has got an inverter over here. So it's very likely that this particular gate structures will have a repeated distortion which looks something like this, because they are exposed to same kind of structures. So while fabricating this one, you fabricate the nearest gate, which is again an inverter. Okay, that's the advantage of being in the middle side. But if you see on this particular edges, this particular inverters and these inverters are connected, might be connected to some flops or some different structures. So basically something like this, I said that this could be a part of your data path, and as a result of that, the inverters at these sides could be connected to a different structure. So in that process, if you see a variation of something like this at the center, you might see a very different variation for the gates that are sitting on either side, and it could be something like this. If you see over here, it could be something like this. Okay, so it is possible that the gates in the middle will have structure something like this, and it's possible the gates towards the end will have structure modified, not similar to ones which we have at the center. And these are all because of various structures that is sitting over here. So the structure that is sitting over here and that is getting fabricated will impact this particular gate. The structure that is sitting over here and that is getting fabricated will impact this particular gate while fabricating, whereas these structures are all bounded by inverters on either side. So you'll get a very periodic structure over here, but towards the sides you might get something like this. So this is one sources of variation. Now how does this W and L affects, what does that actually affects? Okay, so if you look into the drain current equation of an inverter, of a MOSFET, of a single MOSFET, so this is the drain current equation. It's like mu Cox. Cox is the oxide capacitance, W by L the gate voltage, minus the subtract voltage multiplied with the drain to source voltage, minus VDS square by 2. So this is the basically drain current equation of any gate or of any MOSFET or of any transistor. So if you see, the drain current is directly related to your W by L. So any variation that you see in the W and the L will directly impact the drain current. So now the question is, how does impacting of the drain current impacts your delay of the inverter? We'll be looking into that. That is a very interesting point that we have to bring it over here. So in the first of all, we are not done with the sources of variation. This is one source of variation that we saw its impact on the drain current. In the next video, what we'll be doing is we'll look into another sources of variation, which is the oxide thickness. We'll see how does the oxide thickness affects your drain current. So let's try to bring up all of this in the next video. Thank you.